Good afternoon, everybody, and welcome to the second webinar on CCUS, organized by Accelerate and by Acceleric in the frame of Accelerate project. We are given this webinar with the big organizer OGS and the contribution from Sotacarbo, SINTEF, and Tube. So, some recommendation before starting. Please switch off, keep your microphones and cameras switched off. Questions are welcome at the very end of the presentation. We will have a dedicated question and answer session. Please type your questions in the panel. And the speakers will answer you as soon as we will finish the second presentation. Sorry for this. Okay, just a brief introduction on what Excel is. Acceleric is the European carbon dioxide capture and storage laboratory infrastructure. It is based in Trondheim, Norway. It is made up of 5 countries, so Norway, Italy, France, the Netherlands, and the UK. We offer access to more than 79 facilities to the research and industrial community all over Europe. Acceleric is aimed at combat climate changes, so it is an ERIC about energy, and it was based to help Europe meet the Paris Agreement in 2050. So Acceleric is coordinating the Accelerate project. Accelerate project is a 3 years project with a budget of 3.5 million, aimed at facilitating and ensuring the long-term sustainability of the research infrastructure, and to provide some dedicated services to the industrial and research community. And we will offer some activities like capacity building. We will have a dedicated capacity building program, which is composed of 3 main activities. Some will take place starting from 2021. So there will be some specific workshops joined with some schools and some tailored training courses. By now, we have started a webinar series. It has started in October this year. This is the second appointment. The webinar series will be aimed at we'll give some talks on the four themes of the full CCS chain. So we will have talks about capture, transport, utilization, and storage. We will offer 16 talks on very interesting topics. If you want to learn more about Excel, please visit our website. The program is under development, or visit our LinkedIn and Facebook pages. I don't want to lose too much time, so I'm just briefly presenting what you will learn today. You will have 2 fantastic keynote speakers from SINTEF Energy Research, Svend Tollak Munkejord, sorry for my pronunciation, I hope it is correct, and Sigurd Weidemann Løvseth. I will chair the webinar. I will open the webinar, and Lynn Hunter from Løvseth will chair the question and answer session. So I'm just stopping my presentation. I'm just okay. I want to introduce the first speaker. I'm sorry. I want to introduce the first speaker, Svend Munkejord. He is a chief scientist in multi-phase flow, multi-phase flow modeling at SINTEF Energy Research. He has been employed there since 1998. He holds a master's degree in mechanical engineering, a PhD in applied mechanics and thermo and fluid dynamics, both from NTNU. His research interests include mathematical modeling, scientific software development, and experiments. He has worked on operational and safety aspects on CO2 transportation for more than a decade, and including leading the CO2 transport activity in the NCCS Center and its predecessor, the Big CCS. So, Svend, the floor is yours. Please go ahead.
So thank you, Michela, for the nice introduction, and good afternoon, everyone. So my name is Svend Munkejord. I work at SINTEF Energy Research, and the work I'm going to present to you today is performed in the NCCS Center, where you can see the nice logo here. I'd also like to acknowledge my colleagues at SINTEF Energy Research and at SINTEF Industry who have contributed to this, to the nice results. Okay, so the content is, you know, the traditional layout for a presentation. I'll start with the motivation, why we are interested in CO2 transport and injection for CO2. I'll talk a bit about running ductile fracture, which is an important safety consideration that needs to be done for CO2 transport pipelines. Then I'll go on to talk about experiments and modeling of depressurization of a pipe filled with CO2, and in this respect, of course, the first results from the Excel depressurization facility that is located in Trondheim. And finally, I'll conclude. And as far as I understand, questions are welcome, but deferred until after the talks. Okay, so I won't do the general CCS introduction, but as you know, CCS is one of the very important climate mitigation technologies that are needed, and in order for that to work, we will need to transport large amounts of CO2 from capture sites to the stores, and this needs to be safe and efficient. And in order for the engineers to design and operate safe and efficient systems, they need quantification. That is not only a hand-wavy argument, but models providing numbers. This is to decide how to operate the system, how to design it for safety, how to optimize systems, and also in order not to spend too much time, you know, trial and error, or having to do full-scale experiments and so on. And in order to do this, we need models such as flow models, models describing thermophysical properties. We even need numerical methods, which are not always off the shelf. And we need to know things about pipe materials and other materials. One important thing to note is that even though our system under normal conditions will operate in one precise point, we need data and model to cover a wide range of parameters, because we want to know what happens also for off-spec operation. And in order to perform optimization, we need to, of course, calculate derivatives, etc. So we need to span quite a large space of data. And it's important to note that although there are good engineering tools out, they don't for the moment answer all relevant questions for CO2 transport. So there is still work to do, both regarding experimental data and modeling. First, a short note on CO2. I'm not sure how familiar you are, but you know that, for instance, oil and natural gas has been transported in pipelines for years. We have very good models describing this, but there are some differences between CO2, for instance, and oil or natural gas. And that's illustrated here on the right-hand side with what's called a phase diagram, where we plot temperature versus pressure. And that spans out the different states that the fluid can be in. And you see an important region here. I hope you can see my cursor. You have the critical point at about 74 bars. There's a triple point at about 5 bars. Now, critical has nothing to do with safety or anything. It's just what's it's thermodynamics expression, meaning that for temperatures and pressures above this point, there is no longer a distinction between gas and liquid. And at the triple point, we can have gas, liquid, and solid in equilibrium. And these pressures here are such that you may reach them during normal operation. So CO2 transport is very linked to thermodynamics, and we need to take this into account when we design and operate our systems. And there's a lack of flow data for CO2. This is true both for horizontal flow, but in particular for vertical flow, for CO2 injection wells. And since I will talk a bit about running ductile fracture, it's interesting to note that there are good semi-empirical models that are in use for natural gas. They don't work well for CO2, and I'll briefly explain why. Okay, so when you design a CO2 transport pipeline, it has to be designed for various conditions, and including running ductile fracture. And according to design codes, if there is a fracture, it should rest within 1 or 2 pipeline lengths. Now, so when we do that, we assume that somehow you get a hole in the pipeline. This may be because of third-party impact, corrosion, whatever it is, and we want to know, will this hole stay a hole, or will it become a crack that can potentially run for a long distance? And in order to describe this physically, we have to consider what I like to call the fracture race. It's the competition between the pressure propagation speed in the fluid and the fracture propagation speed in the steel. And they are both complicated functions. If we consider the fluid first, the pressure propagation speed, it's related to the speed of sound. And it's dependent on whether the fluid is a gas, liquid, or a mixture of the two. It's dependent on the fluid composition, pressure, temperature, and also the flow configuration of its two-phase. The fracture propagation speed in the steel is also a complicated function. It's dependent on the pipe material, the pipe geometry, also pressure and temperature. Now, if the fracture propagation speed is faster than the pressure propagation speed in the fluid, this will mean that the crack tip here will remain in a high pressure region, and so it will be able to propagate for a long distance. If it's the other way around, the pressure will go down at the crack tip and the fracture will arrest. So those things we want to know when we perform the designs. Here is an example of a simulation that we performed at SINTEF some years ago, and you can see, hopefully, the pipe opens, and in this case, it's an experiment that was performed in a project called CO2 Pipe Trans, and in this case, the fracture propagated until the anchoring of the pipe. You can see here that CO2 is a colorless gas. It can't be seen in this animation. The brown balls you see is a representation of the soil surrounding the pipeline. Okay, so we want to validate such models and make them accurate so that we can perform accurate design. In order to do that, we scrutinize the phenomena, as you can see illustrated here, both from the modeling side and from the experimental side, which is an important point. Now, there is a two-way coupling between modeling experiments and the phenomena. First, as you know, we need experiments to develop and validate models, but actually there is a coupling also the other way. When we have models that we understand, this can lead also to a better understanding of the phenomena. This is maybe less intuitive, but it's what is used, fundamentally in the particle physics, but also in our experiments. We used models to design the XL depressurization facility, which I will show you in a minute. Now, when we are interested in, for example, running fracture, we can perform burst tests, as you can see illustrated here. If the model works, that's fine. If it doesn't, it's not necessarily easy to know why. So we need to independently validate each submodel. So we consider the thermodynamics. In order to have good equations of state, we need, for instance, vapor-liquid equilibrium experiments done in an equilibrium cell, and Sigurd, I suspect, will come back to this in his presentation. We also need to consider the fluid flow. So we have this depressurization tube, which I will come back to. And we need to consider material mechanics. Here's a split Hopkinson tension bar, which can give strain stress curves. And if we zoom out even more, if we're interested in a CO2 value chain, then we need to consider many things, such as running fracture again, transients in CO2 injection wells, ship loading and unloading, etc., etc. And all of those needs validated submodels. And as researchers, we do as best as we can to fill out this comprehensive map. Okay, so last year, the XL depressurization facility was taken into full use. It is constructed on the roof of the NTNU and SINTEF thermal engineering lab in Trondheim. You can see the tube here. It's on the roof because we didn't have 60 meters available inside. Firstly, secondly, it's best to have the CO2 outside. Now, this tube has been specifically instrumented to capture decompression waves with fast pressure sensors and also temperature sensors. It has in a diameter of 4 centimeters, chosen to have a good compromise between low friction but not too much CO2 inside. And you can see a picture here. So there is a metal cap and an insulation, etc. So this is thicker than the actual tube. On the right-hand side, you can see a vessel, which is also part of the facility. The picture was taken before it was finally insulated and connected to give you an impression. And that is also quite unique. For instance, it has it has a setup which lets us measure the outflow using scales. And it has been designed to develop and validate vessel models and thermodynamics models. Okay, so brief recapitulation. The work on the depressurization facility started already in 2012, at which point there was virtually no open data for depressurization of CO2 tubes. Now, in this year, there are some publications that have been made, but still relatively little high quality data available. So there's still good use for this facility to produce data in various relevant configurations. So when we designed the facility, we particularly thought about validating the fluid part of the SINTEF coupled finite element CFD model for fracture propagation control, which I showed you the simulation from, and which you see an illustration of here to the right. But the data can also be put to good use in developing 2- and 3-phase flow models more in general, relevant for CO2 processes and CO2 transport. And we can perform experiments also with varying orifices at the outlet, and thus give insights into outflow and valve modeling, which is needed because valves are often characterized only with water, and which is very different, of course, from CO2. And it can also give insights into heat transfer modeling in pipe flow. So now I'd like to talk to you about the first series of depressurization tests that we performed last year and this year, and which was published earlier this year. and you can see the link. The link here, and it's an open access paper, and in the spirit of Excel, the data is also open access. So there are 4 experiments of pure CO2, different pressures and temperatures. And there's also one reference experiment that we did with nitrogen, so to have a pure gaseous experiment. I didn't talk about that, but this depressurization tube, the way the experiment starts is that we increase the pressure very gradually, and at a certain point there is a rupture disk at the end. You can see it when it is complete. It's like this one on the left, and when it ruptures, it becomes like this, and then you have a very fast opening of the tube to the surroundings. And this is detected by the data acquisition system, and it starts logging at a high rate. You can see here on the right-hand side, there's a video. Probably you can't hear the sound. It says just whoosh anyway. And you can see the cloud here is composed of the moisture in the air condensing from the very cold CO2, and also maybe some solid CO2 particles. This is taken from the street. By the way, this facility has been very thoroughly assessed with respect to safety, since it's at the campus in Trondheim, and we are certain that it's safe to operate. Nevertheless, the experiments are normally done after the normal working hours. Okay, so here you can see an illustration of the instrumentation. Now the opening is here on the left-hand side, where there's a disc holder, and you can see that the pressure sensors are very densely mounted towards the end of the pipe. This is in order for us to be able to capture the pressure waves and to calculate the wave propagation speed. Here in this sketch, you can see that at certain points we have 3 different temperature sensors at different positions, at the top, at the bottom, and the 3 o'clock location. And this gives a certain insight if there is a stratification of the flow inside the pipe, and that has proven quite useful in the experiments we've done so far. So as I said, the data are quite high resolution, so the logging system logs the pressure at the microseconds intervals, and the temperature sensors are logged at a 1 millisecond interval. And this is done during the first 9 seconds, where most of the fast phenomena occurs, and then the frequency is turned down in order for the data amounts not to be too big. We've also performed modeling studies in order for us to better understand what happens in the experiments. So I don't have time here now to go into the details of the model, but I'd just like to briefly mention that we've been using a transient homogeneous equilibrium model, which takes into account the 1 or 2 or 3 phases of CO2, so gas, liquid, and solid. And a homogeneous equilibrium model assumes that each phase has the same velocity, pressure, temperature, and chemical potential, which is in general, of course, not true, but the results shows that it works well enough in some cases. And in other cases, well, that's where we need to do more research. The model has been discretized using a second-order shock capturing scheme. We're using the very accurate Spahn-Wagner equation of state for pure CO2, and for those interested, we're using a Friedel friction correlation and a Gungor-Winterton boiling heat transfer correlation, and we performed the simulations using 1200 or 4800 computational cells. That is quite high resolution. So here you see some sample results. These are pressure plots plotted for the different sensor positions as a function of time. So if we focus now on the right-hand side graph, you can see that initial state here, 120 bars. Then depressurization starts, the pressure goes down. First, it goes down very quickly until you reach this area, and then it goes more slowly. And this is so the pressure propagation has two distinct areas. In this upper area, the pressure waves propagate in single phase, whereas in the lower area, they propagate in the two-phase, which is slower. And you can also see, I forgot to mention, the experiments are the full lines and the calculations are the dashed lines. So in the single phase area, the phenomena are very well captured, since Svend is accurate for CO2, whereas there are more discrepancies evidently in the two-phase area where there are complicated phenomena going on. But still, this is better than what we had hoped for in the beginning. So we can use those pressure plots to generate this kind of plot, which shows the wave speed versus pressure. And this kind of plot is used a lot in the assessment of running ductile fracture. Again, the process starts here on the right-hand side at the initial pressure of 12 megapascal, and then the depressurization goes down to the left like this. At this point here, you can see that there is a split between our lines. So the red line is the experiment. The blue line is calculated assuming full equilibrium. And the green line is calculated assuming that the liquid stays in a liquid phase in a metastable state. So the full equilibrium assumption tells us that at a certain point where you hit the two-phase area, there is a split in the wave speed from the single phase fast wave speed to the much slower two-phase wave speed with a discontinuous procedure like this. And interestingly, the experiments lie in between the two, so between full equilibrium and complete non-equilibrium. What you can also see is that there is not too bad agreement actually with the wave speed here in the two-phase area. The dots here, they mean that we don't have data points from the experiments here, but somehow the process evidently goes from the point here to the right and to the left. So when we assess running ductile fracture, there is in those assessments, you often hear researchers write about the plateau pressure, and this is this plateau described by the blue line here, taken from equilibrium. And you can see that actually the data are significantly below that, which means that this can be taken into account to avoid too much over-design of the pipes. Okay, that was it for the pressure. Now I'd like to briefly talk about the temperature. So similar plots here, temperature for different times. The left-hand plot is taken at the leftmost position of the pipe, that is very close to the outlet, whereas the right-hand side plot is for the closed end of the pipe. You can see there is a very different behavior between the 2 points. Now, if we start with the left-hand side plot, initially there's a very different, very fast pressure decompression. Then it goes more slowly when you reach the two-phase region. And then there's an interesting thing going on here at about 5 seconds. That's where the liquid is completely boiled, and where the temperature starts rising again. And you can see that the time of dry out is relatively well described actually by the homogeneous equilibrium model, even though the temperature is a bit lower than observed. Now we see at the closed end of the pipe that the behavior is quite different. This is because we have no flow there evidently. So the temperature goes down, and you can see that the pressure sensors, they register a jag here at -60 degrees more or less. And this is where in our interpretation we reach the triple point and where the solid CO2 that forms. And the three lines here, I don't know if you see the colors clearly, but we have different temperature readings between the bottom and the top of the pipe. So the bottom is the coldest, and it's quite close to the calculations. And this is indicative of dry ice remaining at the bottom of the pipe at a very low temperature, close to -80 degrees. Okay, so I also like to show you some readings from the middle of the pipe. There you can see that there are more discrepancies between the homogeneous equilibrium model and the experiments. But this is also expected, because here we would expect there to be flow stratification and other things not included in the model. But I'd like you to focus on the right-hand plot here, where again, we can see that there are differences between the top and bottom temperature readings. And this is indicative of flow stratification. That is, the upper part of the tube is in a gas phase, which is not so cold as the liquid phase at the bottom. Okay, so that was a brief insight into our results. So I'd like to conclude here. I'd like to conclude by saying that in order to de-risk CO2 transport and injection, we need physical quantification, and that in turn requires models and experiments at the appropriate levels. And differently from several other applications, the models for transient flow of CO2, they need to be particularly robust due to the process's proximity to the critical point and the triple point where there's lots of thermodynamics, so to say. So we fill in the knowledge gaps, and thereby we want to facilitate the CCS deployment. We've seen that the Excel depressurization facility is producing high quality pressure and temperature data fit for model validation and development. And I've also shown you that the homogeneous equilibrium model can give good results, but not always, so there's still work to do there. And we've also seen that to describe rapid depressurizations, we need non-equilibrium models. So I'd like to end here. Thank you for your attention, and if there are any questions at the end, I'm happy to take them. Thank you.
Thank you very much, Svend. A very interesting presentation. I encourage all the attendees to type their questions in the panel, and we will have the question session at the end. And it is my pleasure to introduce now Sigurd Weidemann Løvseth, who is a senior research scientist at SINTEF in energy research. He has been working on CCS-related research here since 2009, especially on thermophysical properties of fluids. He has managed and designed the construction of a number of advanced experimental facilities, four of which are included in Excel. He had led a number of research projects within CCS. Among other tasks, he is currently managing the R&D activity within the thermophysical properties and physical metering in the Norwegian CCS Research Center and CCS. He holds a master's degree in technical physics, a doctoral degree in fiber optic sensor technology, and as well as 4 patents. So, Sigurd, thank you. The floor is yours.
Thank you for your introduction, Michela. I hope you can see my screen now. This is the second part of this webinar on safe and efficient CO2 transport and injection research. I will focus a little bit more on the fluid properties, following up the introduction given by Tollak. Let's see. So I will say a little bit about what thermophysical properties actually are and why they are important, and the impact of impurities, as well as the data estimation for for fluid properties with impurities. And finally, I will briefly introduce some Excel SINTEF facilities that exist that address fluid property research. So, thermophysical properties, what are they? They are often divided up into two groups that are thermodynamic properties and transport properties. That's the groups I will talk about today anyway. And thermodynamic properties are defined as characteristics features of a system capable of specifying the system state. These properties are derived from what we call equations of states, which are models for thermodynamics. And important examples are phase equilibria, density, heat capacity, and so forth. Transport properties are properties that describe how heat or flow, well, they affect, for instance, transportation of either heat or mass. And examples include viscosity, heat conductivity, and diffusivity. And today I will focus on phase equilibria, density, which is probably the most important thermodynamic properties, and viscosity. So phase equilibria, as Tollak already introduced this diagram, it shows the phase behavior of pure CO2. What the study of phase equilibria can provide is the temperature and pressures at which we have a transition from one type of phase to another. For instance, from gas to liquid, called the bubble point or dew point curve. These the different transition curves for CO2 meet up in the triple point, where you can both have solid, liquid, and gas. And the vapor liquid equilibrium curve ends up at what we call the critical point. What can be noted here is that the typical or very relevant technology ranges for CO2 transport are quite close to this phase equilibrium line, and hence small changes in temperatures and pressures could be of high importance for the properties of the fluids to be transported. That was for a pure fluid. If we add a second component or many components, the phase diagrams are no longer that easy, because what was before curves becomes envelopes, what they call envelopes. That means areas in temperature and pressure where two phases can't coexist. And it turns out that the phases that are present, they don't necessarily have the same composition as the total composition. So that means we need to also determine what the composition of, for instance, in this case, the liquid and the vapor phase is. Further, the second thermodynamic properties that is very important is density. It's important, of course, because it determines how much volume you need to transport a given mass of CO2. And again, you can see that the changes are quite rapid in technology relevant regions, especially for instance, pipeline transport. Viscosity is the resistance of a fluid to flow, basically. Cold syrup has quite high viscosity, warm syrup has low viscosity, to pick an easy example. And this property is quite important whenever you have what we call laminar flow. That means flow without turbulence, which we would have, for instance, in reservoirs. So why are these properties important? Well, I can make a very long list of different processes in CCS where fluid properties are important. Today, I would like to focus on transport of CO2. And here, for instance, if you want to pump or compress your CO2. The power needed is very much dependent on the density. The same with physical metering. If you have fluid volumetric measurement principle, for instance, in order to turn that into mass, you need density. A very important example is corrosion. Corrosion will happen if you transport CO2 with, for instance, a carbon steel pipeline, which is quite common. If you get a water-rich phase, and that is basically a result of phase equilibria processes. And also, as Svend Tollak mentioned, we have this pressure plateau, which is kind of upper limit for the pressure during depressurization, is also dependent on the phase equilibria. And also, you would like to transport the CO2 in a liquid state, and the pressure we have a pure liquid state depends also on phase equilibria, and hence the design of pipelines are also knowing the phase equilibria is needed in order to get a good estimate of the required pipeline thickness. And in ship transportation, you normally transport the CO2 at the low temperatures to reduce the pressure, but that also means that you're quite close to states where you can get freeze out of pure CO2 as dry ice, but possibly also having hydrates or ice formed, and that is all these processes are highly are not desirable because it can cause plugging. So my answer to this question would be that fluid properties are needed in most CCS processes, and for instance, CO2 transport property uncertainty mandates excess margins, so it's very important to reduce these uncertainties. Impurities, there are impurities in CCS from the source, sometimes in very high or large concentrations. These numbers are from IPCC. Of course, if you want to transport your CO2, you can condition and purify your CO2, which was suggested for the now cancelled Mongstad transport project, and also in the current Norwegian full-scale project, where the transport part is called Northern Lights. This CO2 is, well, I would say food grade, so it's very clean, but it has a cost to get it that clean, and impurities will anyway be present during the capture or conditioning process, and you might encounter further impurities downstream or in the reservoir, if not before. So realistic optimization of CCS requires reliable models for impure CO2, and such reliable models require experimental data. So what impact does these impurities have on the properties? We already shortly visited the impact that impurities could have on the phase equilibria. Here are some the impact of some other impurities shown with 5% of each component in binary mixtures. And for instance, for CO2 and nitrogen mixtures, which shown in the blue curve here, you have an increase in the maximum or the minimum pressure needed in order to ensure single phase behavior. And again, that's important for a range of processes. For viscosity, we have here plotted the ratio between dynamic viscosity of a mixture to pure CO2, where we have added 5% nitrogen to pure CO2 in the mixture. And as you can see in this region, at pressures and temperatures, again, very relevant for CO2 transport, you have huge impact of this small amount of impurity. Another thing you might notice is that there is quite a big difference also between the moles, and we'll come back to why later on. but you have basically the same impact on impurities also for other bulk properties, like, for instance, density. The data situation for thermodynamic properties has been fairly well mapped during the last few years, for instance, by Ruhr University Bochum, who makes reference models for CO2-rich mixtures, and also by ourselves in a fairly recent publication. With regard to phase equilibria, this gave a somewhat crude overview, I would say. It shows the modeling that type of mixture models that this reference model I mentioned are using. Where yellow and orange denotes fairly advanced mixture models, which probably means that there are some data, whereas the green and gray ones are very simple models, which indicate there's actually no data. But also when we look at these yellow regions, as we will see in the next few slides, the data situation is far from perfect. And this is one example where we recently measured the binary VLE of CO2 and CO, carbon monoxide. At this temperature, there were actually no data, and hence the models were not that accurate either. So you need actually data to get accurate models normally. For C2 argon, there were some data made in the 60s, and I guess some of you know about this reference model for a thermodynamic model for natural gas called GERG 2008. When this model was made, there was this one data set, as mentioned, from the 60s available, and they fit the model perfectly to those data. The problem is that since when more measurements have been made, none of those measurements actually match the original data from the 60s. And here at 0 degrees Celsius, the impact is quite large. If you go to 25 degrees Celsius, the impact is actually huge. It's like, yeah, 100% wrong. So data should always be verified. CO2 water is another example. It's of course extremely technology important, for instance, due to corrosion issues, as mentioned, and formation of hydrates. It's also a quite basic mixture, I would say. It's everywhere around us. And there are quite a lot of data on VLE between water-rich phase and the vapor phase, in particular solubility data for CO2 in water. What there are almost nothing of is actually what is important for CCS, which is solubility of water in CO2, because this actually determines the threshold for forming a water-rich phase when transporting CO2. With regard to viscosity, the data situation is pure is thin for pure CO2. For mixtures, there are some binary data, but not much, and all of them about 7 degrees Celsius, which means that it's not easy to make models for lower temperatures. And for there are also some multi-component sets from the same group. Now I'm talking about liquid data, which again is most important for CCS. What do we do in Excel to address this lack of data? We have a phase equilibrium setup called CO2 mix here at SINTEF. It was designed actually for CCS and for pressures up to 200 bar and temperatures between -60 and 200 degrees Celsius. And also we have made an effort to make the uncertainty as small as we could. We are now also introducing a new facility that goes up to higher pressure. It's called high pressure and complex phase equilibria setup, HPC-PE. And this facility is particularly well suited for water and brine mixtures, where you saw there was a need for data, and also liquid-liquid equilibria. For instance, the equilibria between liquid water phase and liquid CO2 phase. And it's prepared for additional in situ analysis. I would like to mention that we also have a second installation that works together with CO2 mix, which is available in Excel, which can prepare very accurate reference gas mixtures. And using the phase equilibrium facility available, we have covered some systems, not everybody fully, but still, I think this has been, very valuable work, but which needs to be continued. Secondly, or thirdly, we have also a facility for measuring viscosity and density, called Viscdense in Excel, which consists of two capillary viscometer and a densimeter. And the operational conditions that this facility is designed for is also up to 2000 bar and roughly the same temperature interval as the VLE. With regard to the viscosity, the accuracy we aim for is below 0.1%, except close to critical point. So to sum up, new data is great for researchers as it leads to publications, but that's maybe not the most important in itself. But using this data, you can improve models, either simple cubic models or maybe better, more advanced and accurate models like USCG, developed by Ruhr University Bochum. And of course, you can also use the data directly in other ways, internally or via partners. But there are also some side effects that has to be remembered. When you make such publications, the data come into databases if they are at least published in the right place, which means that also third parties have access to these data and can use them to both through the models we make internally and by third parties. It's possible to make better engineering tools. That all of these factors, I believe, would lead to more low cost and robust CCS. So with that, I would just like to acknowledge Excel Eric and also NCCS and Excel infrastructure projects in Norway, supported by Research Council of Norway and a range of other partners, which you can see here. So with that, my talk is at least concluded, and I guess there are not that many minutes left for questions, but
Thank you very much, Sigurd. No, we are a little bit running out of time, but no problem. We have already some quick questions in the panel chat. Unfortunately, Lynn Hunter didn't show up, so I will chair the question and answer session, even if transport is not my my subject. So I hope it will be okay. Okay, great. So I invite Svend and Sigurd to switch on their camera and microphone and to read the questions they have in the panel. I can read them for all of you. So I can start with the first one, which has already been answered. Well, okay, in the panel, but okay, it's good for the public. So from the results presented in the first presentation, it seems that the homogeneous equilibrium model overestimates the real experimental behavior, that is a plateau of the pressure versus speed, the compression curve. If so, it might provide conservative prediction as far as running fracture control is concerned. Is that correct? Svend has already answered this, but I encourage him to do it again for the public. Svend, you are muted.
Let's try again. So yes,
Yeah,
the brief answer is yes, it's correct. Although it would be preferable to have a better description so that we know exactly where we are, because this discrepancy between the plateau and the real behavior will vary with the initial state and etc. So it's not a constant.
Great. Good. Let's go to the second question instead, which is for Sigurd. Do we have a different corrosion levels in case of a transport of CO2 gas rich with different percentage of CO2? Is different the corrosion if you have different percentage of CO2 in the gas?
Yes, it could be. It depends. It depends really on the composition of the gas, how easy you get the water-rich phase formed, and that's basically the research questions we'd like to answer.
Okay. Good.
Because a third component could have impact on the solubility of water, and of course the water concentrations in the gas is also, of course, important.
Okay, great. And last question is for you again. This is an early warning system to identify corrosion even at an early stage. You presented an early warning system.
Yeah, I mean,
can you identify it at an early stage?
Yes, I'm not sure if I completely understand the question, but you could say that predicting when you get the water-rich phase formed is if you can predict that, you can avoid corrosion. And if you have measured the concentrations of water exceeding that concentration, combined, of course, with other components you also identify, then maybe you can say that there should be corrosion there. But I'm not a corrosion person myself. I'm looking at from the fluid side. So whether there exist also other systems to actually directly detect corrosion, that, well, I think it does actually. There are some companies working on corrosion, but I'm not the right person to ask about such systems.
Okay, thank you for your answers. So it's 3 p.m. So if you don't have any other question, I would stop the webinar here. I would like to thank you very much for your presentations, very interesting presentations. Thanks also to all the attendees for attending this webinar. Please follow us on the next. Please follow also the next webinars. You will find the program on Excel website and on LinkedIn and Facebook page. And yeah, the recording of this webinar will be online in a week or so. So you will also have the PDF of the presentation, excluding any sensitive data. So thank you very much, and I wish you a Merry Christmas and a Happy New Year, and see you next year. Thank you very much. Bye-bye.
Thank you. Bye-bye.
Goodbye.